All right, ladies and gentlemen, the day you have been waiting for has finally arrived. We're starting our first mechanism. And here it comes. This one is not surprisingly called hydrohallucination. Why do you think it has such a name? Hydro, each new molecule has a new hydrogen and a new halogen. There you go. That's where I got its name. And I'm going to ask a question I asked last video. What's the weakest bond on this page? Pi. What's it most attracted to? Something positive. Something positive in a very reactive type of molecule that we're supposed to know. Chapter 4. This is one of the 7 blankety blanks. What's the blankety blank? Page 120 or 122. We still haven't figured it out. When are you guys going to tell me eventually where that pKa table is? It's one of the 7 strong acids, everybody. We got to learn our strong acids like now. That pKa table has to be, no. Oh, it's official. The test date has been changed. There was no complaints whatsoever. You got your wish. And I think 3 or 4 people in the other section, thank you greatly. Okay, so consider yourself thanked. Okay, so what do we have here? We have pi, and it's attracted to hydrogen. Why? Because hydrogen is slightly positive, right? So here's your curved arrow. Pi breaks and makes a bond to hydrogen. Sigma between H and I breaks and becomes what on iodine? Ah, see you back there. Nice job. He said lone pair. And we got our cyclohexane with a C. That's one of them. And it's probably just faster to draw it again. And if you put the H over on this side, then the other carbon in the alkene only has 3 bonds and didn't replace the 4th bond with a new bond. So what kind of charge is the carbon in this corner going to have? It lost a bond, and it didn't replace it with a new one. Talk to me. What kind of charge? Do the formal charge calculation. It would have to have a lone pair to be negative, because it only owns 3 electrons right here. Periodic table, carbon owns 4. You were saying this. This would be a unicorn in this question, because where did that pair of electrons come from? Your mechanism didn't say a lone pair showing up on this carbon. Sorry, say it again. What charge does this carbon have now that it has only 3 bonds? No, it's not in group 2, or not in group 3, sorry. It's in group 4. Okay, so it owns half of 6 electrons here. It shares 6. It owns 3. On the periodic table, it owns 4. Class 1. We call that a carbocation. Are you surprised? You're not allowed to be surprised on that one. You might not even be surprised that it's called a tertiary carbocation for the reasons we've learned already. It's got 3 bonds to carbon. Now, the other product, put the H over here. I want it on the downside because that's how it's drawn up there. Good, there it is. And the other carbon is the one with the cation. Is it the same category? In a way it is. It's carbocation. But what's the classification this time? Primary. One of your jobs, other than reviewing stuff we've studied already this weekend, is to learn about carbocation stability and why the tertiary carbocation is a lot more stable than the primary. You have to know before you come back to class on Monday. Watch videos on it. Read the book on it.
Why they call it halogenation? Why they call it?
Because it's, well, we're adding a hydrogen and a halogen, so it's called hydrohalogenation. We will study halogenation as a separate mechanism for test 3. It's coming up, but it's not on our test coming up. The next test. This and the next one are the only mechanisms on this test.
Which one? Halogen?
Test 3,
No.
6.2D in the textbook, we're going to study halogenation, where there's not HBr, but BRBr, or II, or ClCl, halogenation. Different reactions. Don't mess around with your brain. Don't do this to yourself. We're only studying this one, and then the next one, hydration. And the reason why we start with those, they're almost the same mechanism. So we're sticking with the same mechanism. That's why we're doing it early. And the other product you made, each time you made a carbocation, was what happened to the HI? It gave up its H. We've already drawn the H. What happened to the other piece? What is it? I negative. The only reason I'm showing one lone pair is because I'm going to need it. You know how many lone pairs there are. Here they are. I'm showing them all. You do not ever have to show them all for mechanism. That's the only way you get an I minus. You know this, right? Any other I is not I minus. Group 7 has to have 8 electrons around it to be a minus. And it is. It'll always be a halogen minus in this mechanism. I'm trying to answer this question as generally as I can. The halogen can be Cl, Br, or I. Cl, Br, I only. That's your halogen. I'm sorry? Fluorine, the bond between hydrogen and fluorine is too strong. It's not a strong acid. This reaction does not work unless there's a strong acid. Okay? You get no reaction with HF. None. Okay, so what do we got? Tertiary carbocation, primary carbocation, and which one did I say is more stable? Tertiary. That means you make more of it. In the same amount of time, you're going to make more of these, and therefore, you're going to make more of these, because that's the one that comes from this one. That's where you decided major and minor. In this first step, which is really slow. It's a slow step because you're making unstable species. Can you tell me why these species are unstable compared to the original species? Tell me why. Say it again. The structure, yes. What about the structure? No, they're both very unstable regardless of tertiary or primary. They're both very unstable. The carbon has the carbon does not have lone pairs, but you're getting, it has a plus charge, but that's not why it's very, that's a minor reason why it's unstable. I can't say you're wrong. That's the big one. She says it doesn't have an octet. So when making things that have octet violations is never trivial. It's going to be a rate determining step. You ever heard that expression? It's the slow step. Everything else is going to be lickety split fast. Both of those are very, very fast. Red hot. Let me make it a little smaller. That's too small. Okay. Okay, and you can probably guess the mechanism. I bet you could tell me how you get there. Tell me where my electrons start, my arrow, my curved arrow. Where's it going to start? I got to get from these two things to this thing. lone pair on I, and where does it end? And I want to listen very carefully. Where does it end? Okay, it ends at a bond. Okay, so I'm going to do exactly what you said, and it's wrong. Don't do that. I ended it at a bond. At the carbon, that's a good answer. Stop. That's a good answer. She said it ends at the carbon. The answer I wasn't going to be incredibly happy with is ends at the carbocation. A cation's not a thing, people. It's a lack of a thing. Don't point to things that aren't things. It makes a bond to the atom. Make sure it goes all the way to the carbon atom. What do I mean? You want to lose a quarter point? Well, let's do it a half point at a time. You want to lose a half point? Do that. That's just outer space, people. You want to lose a quarter point? Do this. You're saying, oh, yeah, it ends at the plus. No, it doesn't. You want to get the full point? You go to the carbon. Okay? You keep watching that video over and over. Just rewind. You didn't like that one? Why? It was in outer space. You didn't like this one? Oh, it was at the plus. It wasn't at the C. Oh, you liked that last one. It went all the way to the carbon. Okay? And I think that's it. The other product is minor, right? I think in this particular reaction, I'm guessing. I'm confessing I make up a lot of things, but I bet if you did the experiment, it's not that far off. There'd be about a 90-to-10 ratio there. That's how much more stable that tertiary cation is than the primary one. Okay. It's 9 times faster is another way to think about it. To make this one. And the magic word you're going to read about is called hyperconjugation. You got to know what that means by Monday. All right, that's the end of that video.